Okay, it's time for a real pre-cal. We're past the review slash preparing for pre-cal unit and heading into pre-cal. Now, as is often the case in math classes and math textbooks, we're going to kind of start with something that is almost certainly review, and we're going to work our way into other things. There will probably be a handful of new things in this particular lesson and a handful of review things. Yeah, let's start with what is a function. So what is a function? Right? So a function is a relation. And what is a relation? Just we're kind of backing up the review train. A relation is a mapping of one set onto another set. It's two sets of numbers or data in general that has a relationship between, right? One thing is related to the other. Okay, so a function is a relation where for every member of the domain, what is the domain? Well, the domain is possible inputs into the function, right? Inputs. I'm going to need to decrease my pen size a little bit. Domain is possible inputs into the function. It also is traditionally associated with the x variable. It is also the set of all independent values, right? Independent. Not independent. I don't know why I always want to put an A right there. Independent values. So a function is a relation where for every member of the domain, there is one and only one member of the range. NG. Now the range, going with this correlation here, the range is the set of all possible outputs. Outputs. It is typically associated with the y variable. Okay? And it is the dependent quantities. Dependent. It's the dependent quantities, okay? So for every, now, generally when we start learning about functions back in Algebra 1 or pre-algebra, wherever you started learning it, we learned that a domain has a one-to-one correspondence. So if we have something like this bubble diagram, also known as a mapping diagram, then for it to be a function, for every member of the domain, it maps onto one member of the range, right? So this would be an example of a function. Something that would be a non-example if we're talking about mapping, a mapping type diagram would be something like this, where we have a domain of maybe 5, 6, 7, and a range of 1, 2, 3, 4. And then we have these mapped this way, where the 6 gets mapped onto two different things. So this would be not a function. This one is just a relation. So if we have a member of the domain mapped onto two or more members of the range, then it's not a function anymore. So there are two other ways that we kind of think about it. If we're having a list of ordered pairs, so something like this, we'll just do a little small example. It doesn't really matter because this is hopefully review. If not, you can, if you're one of my students, you can of course ask me to slow down and re-explain pieces of it and whatever else in class. And if you're one of my other students, or excuse me, if you're one of just online viewers, then I have some more videos in Algebra 1 and Algebra 2 and even in pre-algebra that go into this topic in more detail. So you're welcome to go back and check those out. If I happen to remember or somebody reminds me in the comments, I can put links to those in the iCard, of course, so that you have easier access. So we have a set of ordered pairs here. When we're looking at whether this is a function or not, we basically want to look, if it is a function, then x does not repeat, right? So that's one way to think about it. So it's, again, we're only mapping for each member of the domain, the x part. It only maps to one part of the range, one member of the range. X does not repeat. Right? So that's what we're thinking about. Now, the third way that we think about is if we're talking about a, whoops, we kind of went crazy there. That's fine. If we're talking about a graph, we use the vertical line test, right? So if we have maybe a couple of relations on here, let's do one that looks like this. Make that green guy there, and then let's do a red one, and we'll do this one maybe like this. So one of these, the green one or the red one, passes the vertical line test and the other one fails it. So for the green one, if we are drawing vertical lines across here, it never touches. Now, I wouldn't be writing this if I was demonstrating it in person. You just can't see it if I'm moving, because I can move my pen across the board all I want, but you can't see it. So it never, as we're going across, it never, whoops. If we're drawing vertical lines, it never touches the graph more than once. But the red one, we can just have a single example showing that if we draw a vertical line here, it touches that graph once, twice, 3 times. So this red one, so X repeats, right? X repeats. It's mapping onto different, for one member of the domain, the X part, it has 3 different places. 3 different places where it's mapped onto the range. So the red one is not a function, and the green one is a function. So that's what a function is. Hopefully that's review. If not, then, and you need more, again, let me know in the comments, or you can let me know in class or anything else, or on our Discord server or whatever else. So that's what a function is. You probably already knew that. We mentioned the domain and the range. When we have a range of values, you're used to listing it, almost certainly you're used to listing the domain something like this, where the domain is X is greater than or equal to 5, or something along those lines, right? You've almost certainly seen this notation, kind of the standard range inequality notation, or whatever notation, whatever name for this notation you want to see. And this is great. This is not as formal of a notation. So we're going to learn a couple of new ones today. We're going to learn, first of all, we're going to learn what's called set builder notation. Let me change colors here. Set builder notation. Set builder is the most formal way to write a domain because I can spell builder. Set builder notation. It's the most formal. And so if we were to rewrite this in set builder notation, this is how we would do it. So we would say the domain. And then to build our set with set builder notation, we start with basics of set builder set notation, which is curly braces. And then we say, okay, we're looking at X. And then we use what's called a pipe symbol. It's kind of a long thing, but the way we read that, we don't really call it pipe in this context. That's what that symbol actually means. When we look at it in like programming or something else, that's what that symbol is. But we read it such that. Okay. So it's X such that, and then for this type of thing, we list just this condition. So this next part, so this first part is, I already said it out loud, but I should put it on the screen as well. I think that would be useful. This right here is the variable that we're interested in. And then the next part right here is the condition. And so the condition, if we were doing this here in set builder notation, we'd just write it just like it is. X is greater than or equal to 5. So this is called the condition. This is often called conditional notation, by the way. That may help you understand that. This is the condition. And then we put a comma because we need one more puzzle piece when we're writing this, okay? And we need X is a member of, and this is kind of a fancy looking E. I'll label that in a second. And for this case, we're going to say it's a member of the real numbers. And for real numbers, you may have seen this before. We use this fancy looking R. And the next thing I'm going to put on here is a list of all the sets that we can have. But let's first label before we get that this fancy looking E, we read that as is a member of. And then this last bit, I'm going to label this. Now, this particular one, I'll put it in parentheses here, although, again, we'll have this kind of on the next slide, if you will. But this is the superset that X is a member of. What kind of number is it? And then we, of course, end our curly brace here. Oh, I forgot to put in parentheses. This one. This particular symbol is real numbers. Now, you probably, so that's a little arrow, and that's a parentheses. I don't know. That's what I was drawing. My pen is too big for small writing there. Sorry. So let's get what all the different supersets are. You've seen these before. You may not have seen all the symbols. So this is back, if you've been in my class before, you probably have seen the real number amoeba, where we kind of draw this thing with the smallest set being the natural numbers down in the middle. Natural numbers, if you'll remember, is another name for counting numbers. So it's 1, 2, 3, 4, 5, etc., and it goes all the way to infinity, right? Natural numbers. And the symbol we use for natural numbers is N. We like to write it with a fancy looking N. Most all these. Now, different textbooks, as I've discussed before, different textbooks will label things differently. I draw a fancy N with a double bar like this. The textbook we're using kind of as a guide for our class also uses the same sort of a thing. You'll see in some books and some online things, they'll just use bold capital letters for these instead. And so you kind of have to learn what your textbook is. But this is what I use, and this is, again, what the textbook we're using uses. So the next biggest set, which is the same as the natural numbers, except it includes 0, is the whole numbers, right? And for whole numbers, it's a big W, right? So we use big W. And I do the double bars on the down strokes because calligraphy. That's how I label whole numbers. Okay? And then the next one is integers. Integers is the first set where we get a different sort of a letter, which we'll see why here in just a minute. Integers. For integers, we use a capital Z. And I, again, use kind of our double bar type of a font to represent it. So integers we use a Z for, and the reason why we do that is because I is taken by something else, which we'll get to in a minute. Integers, if you'll remember, are positive and negative whole numbers. Now, the next set is the rational numbers. Rational numbers, if you remember, there's, formal definition, but the rational numbers are, in plain English, anything that can be written as a fraction, right? So things like 1/2, things like 0.5, things like 36%, things like 5, etc., etc. If it can be written as a fraction, it's a rational number. And for rational numbers, we use a big Q, and you've already seen why we don't use R, because the R is taken by real numbers. We've already spoiled that one. The next one, which lives outside of the rational numbers, is the irrational numbers. And as you might guess, that's why I isn't integers. I is for irrational numbers. Irrational numbers are things that can't be written as a fraction. Things like pi, or the square root of 2, or Euler's number, which is represented by an E, or tau, which is 2 pi, etc., etc. Anything that can't be written as a fraction. And we use an I for that. And I still use the double notation. That one is not quite as nice because it looks like a Roman numeral 2, but in context, hopefully you'll be able to figure out which one's which. Now, the last one, of course, is the real numbers. That's that biggest superset, which includes the intersection, not the intersection, that doesn't exist, the union of all of the rational numbers and all of the irrational numbers together. And of course, that's the real numbers. Real numbers. And we already saw a capital R for those. Okay, so let's do a couple of examples of rewriting a set in set builder notation. Okay, so let's do a couple of examples. We'll call this examples, and this example 1. And let's do this set. We'll list it in kind of just a generic set notation that's understandable but not so formal. 9, 10, 11, etc. Okay, so this is everything 8 and greater, right? Now, just to show that you don't have to use X, we're going to use a different variable writing this in set builder notation. Let's use an N for this one. So we're going to say N such that N is greater than 8. Greater than or equal to 8, right? And somehow I wrote less than. What have I done? How about greater than or equal to 8? And now N this time is not a member of the real numbers because, see, we don't have all this little infinity right here, all this between 8 and 9. So X in this case is a member. Now you could technically do this as integers, as whole numbers, or natural numbers. It's usually best to write it as the smallest set that makes sense. Now, in this case, we don't typically label things as natural numbers. You could. I'm going to use whole numbers, but natural numbers would also be correct here. In natural numbers, whole numbers, or integers would be correct. The only one, though, anything bigger than that, it would not be correct anymore. Okay, whole numbers. Just because whole numbers is more common than natural numbers, but natural numbers would totally work as well. So there you go. That's in set builder notation. Let's do another one. This one, I like these a lot. These are fun. So let's do all multiples of 3. Actually, in the book they use pi. Let's do all multiples of tau. Tau, in case you don't know, equals 2 pi. Okay. So we want to do all multiples of pi in set builder notation. Let's again use another variable just because we can, and just so that you understand that the variable we choose doesn't necessarily matter. Sometimes it does, like if we're talking about domain, it should be X. If we're talking about range, it should be Y. So sometimes it matters, but you can use different variables here, and we're going to make sure that's really clear by using different ones on our examples. So A such that, now, okay, so it's not greater than or less than something, because it can be everywhere, but only multiples of tau. So what does multiples mean? Well, that's a head scratcher. I think multiply makes sense, right? So how about A? A is our kind of counting variable. It's our variable that we're kind of marking space with. A times tau. A times tau would be one multiple. And then if we want all of them, we put it in this big fancy schmancy notation. We say that A is a member of. Now, this time, it's if we want multiples here, we don't want fractions, right? We don't want it to end up being fractions. So we're going to say A is a member of the integers. This time, it can't be any of these same-sized sets. It has to be integers because we have to get negatives in there. Okay, so that's set builder notation. Now, there's another way that is just as common. And in fact, in my experience in college, this was more common to write domain and range and all these types of things. And that is interval notation. Interval notation. This one is very, very common. I actually have started teaching interval notation and making sure that that gets covered in my classes as early even as Algebra 1 and definitely in Algebra 2 because it's so common and it's so prolific. I used interval notation all over the place in my college years. And so let's jump into doing some conversions. This is example. I've lost count of the numbers. I'll let you do it. Well, no, I guess I won't. How about example 3? Example 3. So we're going to convert this into interval notation. So we're going to convert -8 is less than x is less than or equal to 16. Okay, so this is the way we do interval notation. First of all, we go low to high, always low to high, which is important to understand. All right, so we go figure out what the lowest number represented. So the lowest number represented here is -8. So we're going to write down our lowest number. So it's -8. And then we put a comma and go to our highest number. So the highest number we get to is 16 here. Right? Now, we have to, on the outside, say whether it's not including or including. If it is not including, we put a parentheses, a round bracket. If it is including, we put a square bracket. Makes sense? Let's see if it does by doing another one example. Example 4. Let's convert x is less than 11 to interval notation. Okay, so this time, x is less than 11. That means that our lowest number, if we're going low to high, is actually -infinity. So we're going to go from -infinity to 11. Now, we need to know whether to include infinity or not. So here's the easy rule of thumb. We never include infinity because we can never reach all the way to infinity. So infinity is always a round bracket, aka a parentheses. Now, this one is not equal to, so it's also a round bracket. There we go. So let's do one more example, which will give us another symbol. So this is example 5. Excuse me. So example 5, we've got x is less than or equal to -16, or x is greater than 5. Okay, so this can be used. Now this one, we've got some puzzle pieces here. You don't have to do this, but I'm going to go ahead and graph this one real quick, or not really hardcore graph it, but get a little sketch of what's happening, because it can be easier when we get lots of things happening to kind of sketch us a little graph to see what is going on. So for this one, we've got -16 as a point of interest, and we've got 5 as a point of interest. So x is less than or equal to, I'm going to do this not in interval notation, I'll just do it with our bubbles, right, because it's going to be easy to see. X is less than or equal to 16, so it goes this way. Okay, and then this other one is not including, and it goes this way, right? So that's what it's looking like. Now, because of this or, we're interested in when this is true or this is true, so we need to include them both, right? So we're going to go just like we did before, and we're going to go low to high. So the lowest possible number is -infinity, because it goes all the way that way. So -infinity up to negative 16, including the 16. Now we need another symbol here. What we're going to add is we're going to add this big U looking shape. It's not technically a U, but it's basically a U, and it's good that it's basically a U because it stands for union. Okay, let's label that here. This stands for union. All right, so union, and then we pick up where we left off. So we're skipping over all of this mess. Union means we want to include all of this and that. Okay, so we want to go from 5, but not including 5, and then up to positive infinity, never including infinity. There is our answer. Okay, so now that we got some notation bits out of the way, let's remind us of a couple other things with functions. Okay, we're going to look at, this is going to be a longer lesson. I sort of apologize, not really, but it's going to be okay. So we're going to hit a couple more things. We're going to look at function notation as our next bit, which probably is review. If not, then it's not, and that's okay. Function notation. We're going to jump in with some examples. If you need more, let me know in the comments, and I'll either link it in the iCard and get it to you if you're not one of my students, or if you are one of my students, then we can look at it in class. Next is going to be example 6. Yes, example 6. We are going to jump in straight with examples. So we're going to give, let me give myself a little more space, because for the next 2 or 3 examples, we're going to use this function. Written in function notation, we say this g of x, right? G of x. What G is a function of x, and the function we're interested in is this one, x squared plus 8x minus 24. And for example 6, we're going to find the value of g of 6, right? So what we do, in case you don't remember, is what we do to find this is everywhere there's an x, and we know to plug it into x and not some other variable because g is a function of x, right? And so we're going to plug a 6 in. What I like to do is I like to start by putting parentheses everywhere we're going to substitute. That helps us not make mistakes with negatives and all of those things. It just helps keep things nice and neat. And then we're going to plug in what we're supposed to plug in. So we're going to plug in 6 right here and right there. Then we're going to walk this down just using order of operations, right? So 6 squared is 36. 8 times 6 is 42. Plus 42. No, 42. It's not 42. That's a lie. How about 48? Minus 24. Now we're going to keep on walking. I'm going to, because addition and subtraction is commutative, I am going to do this first because it's going to make the numbers smaller. I should really probably be double checking myself with the calculator and whatever else, but that's fine. Actually, you know what? Let's just punch all of this in the calculator. Boodly-loodly-loop. And we end up with 60. This is pre-cal after all, right? So G of 6 equals 60. Now, this applies no matter what we're plugging in, even if we're plugging in an expression. So let's take a look at example 7. We're going to jump straight into the big crazy mess, and we're going to find G of 5C plus 4. Okay, so we're going to do the same thing. We're going to give extra space this time to make sure. Don't forget to bring down the squared. That'd be an easy place to make a mistake. There are several easy places to make mistakes in this particular problem, but we shall see what we shall see. All right, so then we're going to plug in what we're plugging in, 5C plus 4. 5C plus 4. Now, the first bit is a bit tricky, right? because this first bit, what you'd be tempted to do, and what is, if you're making mistakes, this is where you'd make mistakes. What you might be tempted to do, don't write this down, would be 5c squared plus 4 squared, and then plus, and then you distribute the whatever. That's not how that works, right? Because you end up missing an entire term if we do that. I'm going to kind of give me a little bit of scratch paper space up here. Okay, so squared means that thing times itself, right? So this turns into 5c plus 4 times 5c plus 4. So you've got to do that full distributive property using FOIL method, which is technically a shortcut, which I'm not technically going to use, but I'm still going to multiply first, outside, inside, last. So there you go, but I'm not going to technically use the shortcut because this is a video and I don't want to confuse you any more than I have to. At least that's the story we're going with. So you do first, right? 5c times 5c is 25c squared, and then you do outside, so 5c times 4, which is plus 20c, and then 4 times 5c would be plus another 20c. That's where the shortcut comes in, kind of, but we're not going to do that way. And then we end up with last 4 times 4, which is plus 16. We've got like term. Oops, I made a mistake with colors, but that's okay. You'll forgive me, won't you? We got like terms, 20c. And 20c, this one's not alike because the squared, right? So we end up bringing down 25c squared plus 40c plus 16. So that's this whole schmagoigle, right? So 25c squared plus 40c. I don't know why I'm still in that color. Making all kinds of color mistakes. It's a long video. Cut me some slack, maybe. If not, that's okay. Don't worry about it. No problem. We've got to distribute that 8. 8 times 5c is plus 40c. 8 times 4 is plus 32. And then bring down our minus 24. We've got like terms again. Looks like we've got like terms right here with that one. And then we've got that one is alike with those. So we're going to combine our like terms and walk our way down. So g of 5c plus 4 is 25c squared, and then 40c plus 40c is 80c. 80c, and then 16 plus 32 minus 24 is plus 24. I almost said C, just plus 24. All right, so there is that. We have one more thing to talk about in this lesson. I said it's a long one, and I apologize. I don't like to make long lessons, but this just has a lot in here. We're kind of reviewing, plus a lot of kind of foundational stuff that we're going to use a lot later. So we talk a little bit about domain and range, right? So we're going to... The last type of example here is we're going to find the domain of some function. So we're going to find the domain of the following. We're going to do 3 examples. And this is going to be the last thing in this lesson. Let me know in the comments below which you prefer. Eventually, I plan to remake all of these videos and whatever else, so you'll have even more input. Which you prefer, whether you prefer doing it this way and have one kind of long video, or the way I did it in Unit 0, Lesson 3, where I did a big lesson and I chunked it into 4 smaller bits or shorter videos. Which do you prefer? Do you prefer one long video or 3 or 4 or whatever smaller, chunkier videos and splitting it up that way. Let me know in the comments what you prefer, because I can do either one. It does doing several shorter videos just takes me a tiny titch longer to do than this way. And so, you know, there it is. All right, so let's do, what are we at? Example 8-ish. Yeah, look at that. How do I remember that? I don't know. Some strange magic. Example 8. So we're going to find the domain of f of x equals 2x. Oops, excuse me. It wouldn't actually matter. It would be the same domain, but 2x, 2 plus x. I can do it. 2 plus x over x squared minus 7x. Okay, so we want to find the domain of this. So domain is a list of all possible x's. So it's what x can be. Now, when we're doing a problem, we're trying to find the domain of a function. It's often easier if we take a look at this and think about, instead of thinking about what x can be, if we think about what x cannot be. So when we're looking at a fraction like this one, what can we not have? Well, we cannot have an x in the denominator. An x. I'm struggling with words. I don't know. Long videos, not my friend. Maybe I just need some lunch. I don't know. But x cannot be 0. And so what we need to do is we need to figure out that first, and then we'll write it in one of our two notations. We're gonna, in these three examples, we're gonna switch up the notations, do set builder notation on one, interval notation on the other. That way we continue getting practice and whatever else. If I was to give this to you on a test or quiz or something, I would give you how to write the domain or the range in set builder or interval notation. Or if I didn't list it, you would be able to and willing and whatever else to write it in whichever notation you prefer. So back to the problem. Here we go. So in order to figure out what the domain is, we have to say that x, let's change colors, show the work in a different color. X squared minus 7x cannot equal 0, right? So we need to solve this. Now, you would be tempted, I suspect, if you're looking at this, you would be tempted to just divide everything by x. X divided by 0 is still 0, and end up with x minus 7 does not equal 0, and then say x does not equal 7. If you do that, though, you lose an answer. Okay, so don't divide variables into 0 and expect to get all the answers that you're looking for. What we instead have to do, we have a quadratic. Now, we've kind of practiced this before. We have several different methods to do a quadratic. You could technically do this one using the quadratic formula if you wanted to, or even completing the square, but this one is super easy to factor because we have two numbers that have the same thing. What is happening? Oh, let me pause and see. This is one of my students' parents. I'll be right back. Okay, I'm back. Here we go. So this is really easy to factor because we have two terms that have the same variable, so we can use GCF factoring because they both have an x. So we can factor this into x times, and then we divide out that. So x squared divided by x is x. 7x divided by, or negative 7x divided by x is negative 7. So now that's factored. So now that it's completely factored and equal to 0, we split it and set each factor equal to 0. So x cannot equal 0, and x minus 7 cannot equal 0. We add 7 to both sides here and end up with x cannot equal 7, right? So we can list this in interval notation or set builder notation. For this one, it's... This one, actually, if we were listening, this one would actually be longer in interval notation, which is unusual. So we'll do this one in set builder notation because you'd have to have 3 sections in order to list this in interval notation because we have to do before 0 and in between 0 and 7 and then after 0. So to write this in set builder notation, we would list and say the domain. It shouldn't go to white. That's a mistake. How about back to green? x such that x does not equal 0 and x does not equal 7, and then x is a member of the real numbers. Oops. Yeah, no, that's right. That kind of got a little messy. I apologize. I was trying to see if I can fit both of these first two examples on the same page. Maybe that was a mistake. Almost certainly was a mistake. It's a mistake when y'all do it, for sure, or when I do it on paper and whatever else. All right, let's do one more example. Example number 9. We'll use a different set of colors for this one. And if it gets too smushed, we'll copy it onto a new slide and then make our life happen that way. So let's do a different kind. Let's do g of t. We'll make it a function of a different letter this time. This is very common. A function of t, it is very common in physics or chemistry because we very often have things that are functions of time. So g of t equals the square root of t minus 5. So now, just like we thought of up here, we need to think about what x cannot be. Excuse me. And so what can we not have under a radical? Well, we can't have negatives. We can have 0. 0 is fine. We cannot have negatives. So we're going to write our answer in interval notation, but we're going to write it in just generic conditional notation first to kind of think through what's happening. So we've got t minus 5 has got to be greater than or equal to 0, right? So to solve that, we would add 5 to both sides, and t has got to be greater than or equal to 5. Now let's write this in interval notation, okay? So this would be, the domain would be, the lowest number here is actually 5, right? Including 5, because we're going up. T is greater than 5. So from 5 to positive infinity, we never include infinity. Let's do one more example that's going to kind of combine both of those things. So I think it's useful to have that as an example. And we'll do one more in interval notation just to kind of continue our well-roundedness. Okay, so our final example 10. Thought this video was probably going to push towards 45 minutes. But, there you go. Again, let me know in the comments what you prefer. If you like it this way or the other way better. And I can try to, in the future, accommodate that. Let's do h of z. H is a function of z. I don't know what z represents. Some hypothetical nonsense. Equals 1 over the square root of x squared minus 9. Okay, so x this time, we cannot have the denominator equal to 0, and we also can't have it less than 0 because we can't have it be negative because of the radical, and we can't have it be equal to 0 because that would make the whole denominator 0, right? So what we can do is we can set x squared minus 9 as greater than, not greater than or equal to, but greater than 0. So let's do that. X squared, minus 9 has got to be greater than or equal, greater than 0. I'm almost through. We can do it. All right, so there's a couple different ways to solve this one. You could do it as a difference of two squares and factor it. But I'm going to do this one a different way because I want to remind you of something else. So let's solve this one by first adding 9 to both sides. And so then we end up with x squared is greater than 9. Now, to get rid of the squared, what's the opposite of squaring something? Well, it is square rooting something, so we can take the square root of both sides. Now, this is the thing I wanted to remind you of. If you take the square root of both sides, then you end up with plus or minus this, okay? So we end up with x squared is greater than or equal to plus or minus 3. right? Does that make sense? I hope so. Now, the problem is that this, as is here, is a tiny titch misleading because this symbol actually is kind of broken here doing it this way. It doesn't quite end up right. And we're going to use a method that's really common and to use to test which intervals we're interested in, and that is to look at the different pieces of the puzzle and test something in each region. So the places we're interested in are -3, or the numbers we're interested in are -3 and +3. Now, what this is written is x squared, or no, that's wrong. Made a straight up mistake. How about we just say x is greater than or equal to 3, which would be like just this, right? But that's not actually the answer, because they don't all work that way, right? So first of all, we're going to have filled in circles or square brackets, pretty for sure, right? Pretty for sure, because it can be equal to 3 and -3. That much, no. I keep trying to make it equal. What am I doing? What am I doing? It cannot be equal. How about it can be not equal? That makes much more sense. Now, let's do a little test here. So we need to pick a number in each one of these sections that are laid out now. So we're going to pick, how about -4, 0, that's going to be the easiest, and let's pick +4. And let's plug these in and see if we get a true statement for these things, and see if we can figure out where this graph, or where the domain, where this set, all of those words actually lives and exists. So when we plug -4 in here, -4 squared -9 is greater than 0. Almost put equal again. So -4 squared would be +16 minus 9. 16 minus 9 is greater than 0. 16 minus 9 is, of course, 7. Is 7 greater than 0? Yes, it is. So this one works. Okay, let's plug a 0 in here. That's going to be easy. 0 squared is 0 minus 9. Is that greater than 0? 0 minus 9 is -9. -9 is not, in fact, greater than 0. This one doesn't work. Let's do our third and final one. We're going to plug a +4 in here. +4 in here. 4 squared minus 9. I think you may be able to see where this is headed, but we'll walk it out just in case. 4 times 4 is 16. Minus 9, is that greater than 0? 7 is greater than 0. This one works. So if we were to write this as a conditional, then x would be greater than, no, LOL, would be less than -4, and it would be greater than 4. So if we write it as a conditional, this is how we'd write it. If we put it in set builder notation, we would shove this into the x such that blah, 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 blah. Well, let's write this in interval notation so we can get one more practice with that union thing. So our domain, our final answer here is our domain is -infinity, never include infinity, all the way to -4, not including, for the 50 bazillionth time, trying to remind myself, and the union of everything over here, which would be 4 to +infinity. And there we go. So there is our review / learning about some functions with some notation and some other bits and bobs. In our next lesson, if I'm not greatly mistaken, we're going to be talking about analyzing graphs of functions. We're going to look at some pretty pictures and see if we can understand what they mean, which is very useful for statistics and for physics and all kinds of other things, and pre-calculus too. I shall see you there. Let me know in the comments how we can help you with math, science, or general homeschooling, or any of these other things. And don't forget to hit the like button and subscribe to Ember Learning Labs for more content. Words. Great time.